Ladies and gentlemen, a warm welcome to the inaugural session of the 5-day National Workshop on Applied Mathematics and Computing organized by Madhav Institute of Technology and Science, Gwalior. We are honored to have esteemed speakers, dedicated faculty members, and participants joining us for this enriching event. Allow me to provide you with a brief introduction to MITS and the Department of Engineering, Mathematics and Computing. MITS was established in 1957 by His Highness Sir Jivaji Rao Scindia, Maharaja of the erstwhile state of Gwalior under open door policy of Government of India. The foundation stone of institute was laid by the President Dr. Rajendra Prasad and has since been a pioneer in providing quality education. The Department of Engineering, Mathematics and Computing, founded in 2020, aims to impart knowledge in mathematics and computer science to groom the academic potential of students and keep them abreast of recent technological developments. The core objective of this workshop is to facilitate knowledge sharing through research oriented lectures by renowned experts in graph theory, fuzzy inventory model, cloud computing, and machine learning. The workshop aims to create a platform for information exchange and training between researchers for different generations focusing on the application of mathematics in computing fields. Now, I would like to take a moment to acknowledge the efforts of Dr. Atul Kamal Ray, Assistant Professor in the Department of Engineering, Mathematics and Computing, who has played a pivotal role in organizing this workshop. I invite Dr. Ray to say a few words about the workshop objectives and the importance of applied mathematics in computing. Over to you, sir.
Okay, thank you. Thank you, Parth. Namaskar, everyone. On the behalf of Head of the Institute, Dr. Atik Mitse, Director MITS Gwalior, and Head of the Department, Dr. Vikas Sindhas, Professor, Department of Mathematics and Computing, I would like to welcome and thank all the speakers and the participants of the workshop. Also, a special thanks to the committee members and student members of the workshop for conducting this valuable workshop. Thanks to the speaker who approved our request in a short period of time. Actually, the success of this workshop is decided by the number of participants interested or enrolled or registered in the workshop and how much participants learn from the workshop. And I'm happy and proud to say that 700 plus participants have registered in this workshop from different part of the India. It's from different states they have enrolled. So it is a very proud moment for us. And this workshop is already a successful workshop. So that's why we have also taken preferred Geo Meet actually. So I wish all the participants to learn more from this workshop. Thank you very much. Over to you, Parth.
Thank you, Dr. Ray, for your insightful remarks and for your dedication in making this workshop a reality. Esteemed participants, we are honored to have with us today an esteemed speaker who will be enlightening us on the topic of graph coloring and complexities. Allow me to introduce our distinguished speaker, Professor Sharmila Mary Arul. Dr. Sharmila Mary Arul is renowned professor at the Savita School of Engineering, Chennai. With a profound experience of 27 years, she has made significant contribution to the field of graph theory. Her expertise and research focus on approximation algorithm on the achromatic number of graphs. Dr. Sharmila Mary Arul academic journey encompasses an impressive range of accomplishment. She has been involved in various professional activities and serving as the convener of several workshops and lecture series in mathematics. Her dedication to the field of mathematics extends beyond academia. Dr. Sharmila Mary Arul has delivered expert lectures, reviewed research papers, and conducted workshops on various mathematical concepts. Her expertise and contribution have earned immense respect. Now let us eagerly listen to Professor Sharmila Mary Arul as she takes the stage to enlighten us with her expertise and insights. And participants, we will be sharing quiz attendance form as well as feedback form from in by the chat during the session or after the session. So be attentive and attend it curiously. Over to you, ma'am. Ma'am.
Are you there, ma'am? Okay. Yes.
Are you able to hear me?
Yes, ma'am,
Yes,
for
yes,
sure.
yes, ma'am. Clearly.
Thank you so much for the words. I'm really happy, and it is a great honor to come and have the sharing of the knowledge. And at this juncture, I would like to thank Savita School of Engineering Management for allowing us to give this kind of a talk. Thank you so much. Are you able to see?
Yes, ma'am.
So today I'm going to talk about graph coloring and complexities. Actually, it is just an ocean when you jump into this graph coloring concept. So knowing graph coloring is just like a child play, but it is very, very vast. So during the talk, I'll be just explaining all these things. So I'm just dividing the sessions into 5 portions. So session 1, I'll be talking about the introduction to graph coloring. And session 2, I'll be talking about graph coloring algorithms. And session 3, I'll be talking about complexity classes and graph coloring. And session 4, advanced topics in graph coloring. And session 5, conclusion and further reading. So let me move on to the topic of introduction to graph coloring. So let's see how the graph coloring came into picture. So this is a map we are having, and we wanted to color this map. So how do we color? So each state will be given different colors, adjacent state will be different colors, then only we can call this as the coloring of a map. So for example, in this, we are having the adjacent states were colored in different colors, and if you consider each state to be the vertex, and the adjacent vertices, if there is a maybe I can say if the states are adjacent with each other, then you will be having an edge between those two vertices. So like this, the map will be converted into a graph. So coloring of maps will be converted into coloring of graphs. So for example, you are taking some simple graph here given, and how many vertices are there? 5 vertices are there, and if you just remove the pendant vertex which is on the leftmost side, you are having 4 vertices, and it is looking like a complete vertex, complete graph on 4 vertices, and we just need to color this simple graph with the condition that no 2 adjacent vertices will receive the same color. If I concentrate only on the complete graph on 4 vertices, I'll be checking whether this is a correct coloring or not. See, we are having 3 colors, and of which the 2 colors maybe on to the rightmost side, the edge, you will be having both colors to be of the same color. But it is not so. That is a brown, light brown, and this is a dark orange color. So how many vertices are there? There are 5 vertices. How many colors? We need minimum number of colors only we are going to see. So the minimum number of colors satisfying the condition of I know 2 adjacent vertices receive the same color will give rise to the definition definition of chromatic number. So what do you mean by achromatic number? You have to have the first condition, no two adjacent vertices will receive the same color. Also, every vertex should have an edge between every other vertices. Along with that, when you have the maximum number of colors, you'll be having the achromatic number. So the next one, we are moving on to the graph, is a planar graph. If it can be drawn in the plane, where without any edge crossings, and we are having the four color theorem. For every planar graph, we have the chromatic number will be less nor equal to 4, and it is found in the year 1850 and finally proved in the year 1976, and it is given here. Next, we will see the overview of graph coloring. So what is the graph coloring definition? Graph coloring involves assigning colors to the vertices of graph subject to the certain constraints. So mathematically, we can represent a graph. We know very well that G is equal to V comma V, G equals to V comma E, where V represents the number of vertices and E represents the number of edges here. The next one, we'll be seeing about the definition of vertices and edges of a graph. A graph is a collection of vertices and edges. Vertices represent distinct elements or entities, while edges represent connections or relationship between those elements. The next one, we are having coloring constraints. No adjacent vertices can have the same color. So when coloring the vertices of a graph, we impose a constraint that no two adjacent vertices should have the same color. Mathematically, if we have two adjacent vertices U and V connected by an edge U comma V in the graph, they should be assigned different colors. Then what is the goal? Our goal is to minimize the number of colors used. The primary goal in graph coloring is to minimize the number of colors required to color the graph while satisfying the coloring constraint. The minimum number of colors needed to color a graph is known as the chromatic number of a graph. Mathematically, we define a proper vertex coloring function, C from V to S, where C of V represents the color assigned to a vertex V and S represents a set of available colors. The coloring function should satisfy the following conditions. And we know very well that no two adjacent vertices should receive the same color, and hence we have C of U not equal to C of V for every edge, U comma V and E, and ensuring that adjacent vertices have different colors. And the number of distinct colors used, mod S, should be minimized, representing the goal of minimizing the number of colors. So by finding the optimal coloring that satisfying these conditions, we have effectively colored the vertices of a graph while minimizing the number of colors used. Remember to include appropriate coloring system so that it will be easy for you to find the answer in an algorithmic way. Next, we will be moving on to real-world applications of graph coloring. So let's explore the real-world applications of graph coloring. And the first one, we are having register allocation in compilers. So in compilers, register allocation involves assigning variables to a limited number of registers into a computer processor, and it can be modeled as a graph coloring problem. Here, the representation goes like vertices V represents, each vertex represents a variable or a location where the data is stored, and edges E represents an edge exists between two vertices if the corresponding variables are live simultaneously and cannot be assigned to the same register. And here the goal is to minimize the number of registers required to store variables by assigning the colors or the registers to vertices, that is a variable, in such a way that no two adjacent variables connected by an edge share the same color, that is the register. The next point is nothing but timetabling and scheduling problem. Timetabling and scheduling problem involve assigning resources such as classrooms, time slots, or machines to a set of activities subject to certain constraints. This can be modeled as a graph coloring problem. Let us consider a simplified mathematical representation, and each vertex represents an activity or a task, and each edge exists between two vertices if the corresponding activities cannot be scheduled simultaneously due to resource constraints. The objective is to assign colors, that is resources or time slots, to vertices, that is activities, such that no two adjacent activities connected by an edge share the same color, or that is the resource or the time slot. Point number 3 says frequency assignment in wireless communication. So let's see how it is working in wireless communication. Frequency assignment involves allocating frequencies to different communication channels in wireless networks to avoid interference. So mathematically, again, when we move on to this, each vertex represents a communication channel or frequency, and an edge exists between two vertices if the corresponding channels are in close proximity, and using the same frequency can cause interference. So here again, the goal is to assign colors, that is the frequencies, to vertices representing communication channels in such a way that no adjacent channels that is connected by the edge share the same color, that is a frequency, to minimize interference. The next one is nothing but map coloring and Sudoku puzzles. Both map coloring and Sudoku puzzles can be modeled as graph coloring problems. So let us focus on map coloring. Each vertex represents a region or area on the map, and an edge exists between two vertices if the corresponding regions share a bound. The objective is to assign colors to the vertices, that is regions on the map, in such a way that no two adjacent regions that is connected by an edge share the same color. The minimum number of colors required to color the entire map is known as the chromatic number, and these applications demonstrate how graph coloring represented mathematically can be used to solve practical problems in various domains. Next, we move on to the terminology and notation section. So we are moving on to proper coloring. In this simple graph, we are having two examples. Example 1 is on the top and the example 2 is in the bottom. So G is a graph. Color the vertices of G such that adjacent vertices are assigned different colors. So for example, if I consider the first graph, how many vertices are there? 4, 5, 6 vertices are there. So easily I can color the graph with 6 colors. But what is my aim? My aim is to reduce the number of colors if it is an achromatic number. But this example shows only a proper coloring. No two adjacent vertices should receive the same color. In the same manner, when you see the second example, if you consider only the first part alone, it is nothing but a complete graph on 4 vertices. So obviously 4 colors are needed, and a pendant vertex you have. So the pendant vertex can be colored by any one of the existing colors other than 4. The next one, complete coloring. So G should be a proper coloring, as well as every pair of colors I and J, there are adjacent vertices U and V colored I and J. So it should be satisfying the condition of proper coloring, as well as you will be having additional constraint, then only it is called as a complete coloring. So we have to keep it in our mind, saying that no two adjacent vertices should receive the same color. That is only the proper coloring. And then you will be applying the additional condition for every pair of colors ij. There are adjacent vertices uv colored ij. For example, you are having 4 colors, and the 4th color should have an edge between first color and the 4th color, second color and the 4th color, third color and the 4th color. So then only it will be giving rise to complete coloring. So let's move on to the next one. What is the exact definition of chromatic number? The chromatic number of a graph, denoted as chi of G, is the minimum number of colors required to color the vertices of graph G in such a way that no two adjacent vertices share the same color. In other words, it represents the minimum number of distinct colors needed to achieve a proper coloring of the graph. So what is the definition of proper coloring? A proper coloring of a graph is an assignment of colors to its vertices following the coloring constraint that no two adjacent vertices should receive the same color. In other words, for any two adjacent vertices u and v connected by an edge in the graph, their assigned colors c of u and c of v must be different. And the normal notations what we use in graph is nothing but we'll be starting with the graph G. The symbol G often represents a graph with vertex V and edges E. And the next one we will be going in for the vertices. The symbol V is used to represent the set of vertices or nodes in a graph, and it can be written as V1, V2, V3, etc. And E represents the edge. The symbol E is used to represent the set of edges in a graph. It can be written as E equals to, we'll be combining V1, V2, V2, V3, V4, V3, V4, etc., where each edge Vi, Vj connects vertices Vi and Vj. By using these notation consistently, it becomes easier to discuss and to describe graph coloring problems and their solutions. So let's move on to example of graph coloring. So here I have picked up one small graph with vertices A, B, C, D. So the first one, if you consider only A, B, C, it is a kind of a triangle, or in other words, I can say that this is a complete graph on 3 vertices. Obviously, 3 color will be needed, and the last vertex D can be colored by the color whatever we are having for the vertex A. Then it will give rise to the chromatic coloring. So in order to explain this in a very simple manner, I have got 4 figures where the first one represents A, B, C, D, and you are replacing the edge, replacing the vertex A by the color R, and then you are replacing the vertex B by color G and C by B, and then you are having the last vertex D to be the color R. There is a mistake. So it should be color R for chromatic number. Next, we are moving on to the session 2, graph coloring algorithms. Graph coloring algorithms are mathematical techniques used to assign colors to the vertices of a graph in such a way that no 2 adjacent vertices share the same color. This coloring process follows certain constraints and aims to minimize the number of colors used. So in a graph G consisting of V, E, a proper coloring is an assignment of colors to vertices such that no 2 adjacent vertices share the same color. The chromatic number of a graph is the minimum number of colors required to achieve the proper coloring. And the graph coloring algorithms play a crucial role in solving various real-world problems that can be modeled as graph coloring problems. Some examples include register allocation in compilers, timetabling and scheduling problems, frequency assignment in wireless communication, and map coloring. These algorithms employ different strategies and techniques to find the valid colorings of graph. Commonly used graph coloring algorithms include the greedy coloring algorithm, backtracking algorithm, genetic algorithm, and many others. So let's start with few algorithms. Let's start with greedy algorithm. The greedy algorithm, coloring algorithm, starts with an empty list of colors and assigns colors to the vertices one by one in a specific order. It aims to assign each vertex the smallest available color not used by its adjacent vertices. And of course, first I will just tell about all the algorithms, then we will be going in detail about the greedy algorithm. The backtracking algorithm explores all possible color combinations through the depth-first search strategy, and it assigns colors to the vertices recursively, and backtracking when conflict arises and trying different color assignments for previous vertices. And the genetic algorithm takes inspiration from natural evolution and genetics. It uses a population-based approach and genetic operators such as selection, crossover, and mutation to iteratively improve the fitness of individual representing color assignments. So each coloring algorithm has its own strength and limitation. Some algorithms prioritize simplicity and efficiency, while others focus on finding optimal or near optimal solution. The choice of algorithm depends on the specific requirement of the problem, the characteristics of the graph, and the trade-off between the solution quality and computational resources. By applying these mathematical algorithms, researchers and practitioners can tackle complex graph coloring problems and find efficient and effective solutions in various kind of domains. So when we move on to this greedy algorithm, it is a simple and straightforward approach for graph coloring. It iterates through the vertices in a specific order or by degree of the vertex and assigns the smallest available color to each vertex. The greedy coloring algorithm is a simple and widely used approach for graph coloring. It follows a straightforward process of assigning colors to the vertices while ensuring that adjacent vertices have different colors. And the step-by-step procedure for the explanation of greedy coloring algorithm. First, we'll start with the empty list of colors. In with no colors assigned to any vertex, then you will be moving on to order the vertices in a specific manner. Then you will be going for each vertex assign the smallest available color not used by its adjacent color. Then consider each vertex in the predetermined order. While coloring the vertex, check the colors assigned to its adjacent vertices so that no two adjacent vertices receive the same color, and repeat the steps again and again and again till we get the optimal coloring technique. Continue the process for each vertex in the graph until all the vertices have been assigned colors. So what are the advantages of the greedy coloring algorithm is that it is very simple in nature, so that it is easy to understand and to implement. The second one is efficiency. It is typically has a fast execution time for many graphs and especially for sparse graphs. And it gives a low memory usage. The algorithm only requires storing the list of colors assigned to vertices, resulting in low memory usage. Next, we move on to the limitation of the greedy algorithm. Limitations of the greedy algorithm. First one, suboptimal solution. The greedy algorithm may not always produce an optimal coloring. It can result in suboptimal colorings where more colors than necessary are used. Then the next one, we go for sensitivity to vertex ordering. The order in which the vertices are considered can affect the resulting coloring. Different vertex ordering may yield different coloring and including suboptimal ones. The last one will be lack of optimality guarantees. The greedy algorithm does not guarantee finding the minimum number of colors needed for the graph, that is the chromatic coloring. Despite these limitations, the greedy coloring algorithm is still widely used due to its simplicity and efficiency for many practical applications. It serves as a good starting point and can often provide reasonable solutions for graph coloring problems. So the first one we studied about the greedy coloring algorithm. Next we move on to backtracking algorithm. Backtracking algorithm is a systematic approach that explores all possible color combination until a valid coloring is found. It uses depth-first search strategy to recursively assign colors to vertices and backtracks when conflict arises. So what are its advantages? Backtracking algorithm guarantees finding a valid coloring if one exists. It can handle more complex coloring constraints and irregular graph structures. And what are its limitations? Backtracking can be computationally expensive for large graphs as it explores all possible color combinations. The time complexity of the algorithm grows exponentially with the number of vertices. So now we finished with backtracking algorithm. Let's move on to genetic algorithm. Genetic algorithm is an optimization technique inspired by natural evolution and genetics. It uses population-based approach to find better solutions iteratively. Genetic operators such as selection, crossover, and mutation are applied to create new generation and improve the fitness of individuals. And the advantages, genetic algorithm can handle large solution spaces effectively, efficiently. It is suitable for finding near optimal solutions and exploring trade-offs between the number of colors used and execution time also. The limitations in genetic algorithm is that it requires suitable representation, genetic operators, fitness functions for graph coloring. Turning the algorithm's parameter can be challenging to achieve good performance. So till now we were seeing about greedy algorithm, backtracking algorithm, genetic algorithm, and we need to know the comparison between all the three and the contrast also. Then we can decide on which algorithm will be better for this kind of a situation for our problem. All the three algorithms aims to solve graph coloring problems, but they differ in their approaches and characteristics. Greedy algorithm is very simple and fast, but may not always provide optimal solution. Backtracking algorithm guarantees the optimal solution, but can be computationally expensive for large graphs. And genetic algorithm is efficient for exploring large solution spaces and finding near optimal solution, but requires additional configuration and parameter tuning. So greedy and backtracking algorithms are deterministic, while genetic algorithm introduces randomness through genetic operations. The choice of algorithm depends on the problem's requirements, graph characteristics, and desired trade-offs between solution, quality, and computational resources. So let's go for the conclusion of this graph coloring. The greedy, backtracking, and genetic algorithms are three distinct approaches used for solving graph coloring problems. Each algorithm offers its own advantage and limitation, making them suitable for different scenarios and problem requirements. The greedy algorithm, as I said earlier, is a simple and efficient approach that assigns colors to the vertices, and it aims to assign the smallest available color to each vertex while ensuring that adjacent vertices have different colors. The greedy algorithm is easy to implement and to execute quickly for many graphs. However, it may produce suboptimal solutions and can be sensitive to ordering of the vertices. Whereas the backtracking algorithm is a systematic approach that explores all possible color combinations until a valid coloring is found. It uses a recursive process of assigning colors to vertices and backtracking when conflict arises. The backtracking algorithm guarantees finding a valid coloring if one exists, but can handle more complex coloring constraints. However, it can be computationally expensive, especially for large graphs, as it explores entire solution space. The third genetic algorithm is an optimization technique inspired by natural evolution, and it is efficient for exploring large solution space and can find near optimal solution. However, it requires defining suitable representation operator fitness functions specific to graph coloring problems, and hence it is very challenging. Each algorithm has its strength and weakness, and the choice of algorithm depends on the problem requirements, graph characteristics, and trade-off between the solution quality and computational resources. The greedy algorithm is often a good starting point due to the simplicity and efficiency. It is, if an optimal solution is required, backtracking guarantees finding one, but the cost of increased computation time. The genetic is suitable for exploring large solution space and finding near optimal. Ultimately, the selection of algorithms should consider the problems, complexity, available resources, desired solution quality, and the balance between the computation time and the solution optimality. The third session is complexity classes and graph coloring. What is the meaning of complexity, first of all? Complexity theory in graph coloring can be mathematically explained using concepts such as decision problems, time complexity, and computational complexity classes. Here, a mathematical explanation of complexity theory relevance to graph coloring is given. So first, we will talk about decision problems. So let us consider a decision problem related to graph coloring. So we will start with, given a graph G and a number K, can G be a properly colored using K colors? This decision problem can be denoted as coloring, where coloring of G comma K equals to true if G can be properly colored with K colors, and coloring of G comma K equals to false when it is otherwise. Next, we will be talking about time complexity. The time complexity of an algorithm measures the amount of time it takes to solve a problem instance as a function of the input size. In the context of graph coloring, we can analyze the time complexity of different algorithms used for graph coloring. For example, we can use big O notation to express the worst case time complexity of an algorithm, such as order of f of n, where n represents the input size, the number of vertices and edges, and f of n represents the growth rate of the algorithm. Next, we talk about the computational complexity classes. Computational complexity classes such as P, that is polynomial time algorithm, NP, non-polynomial time algorithm, provide a formal framework for defining problems based on their computational difficulty. P represents the class problems that can be efficiently solved in polynomial time. NP represents the class of decision problems for which a given solution can be efficiently verified in polynomial time. The class NP complete contains the most difficult problems in NP and includes graph coloring as one of its members. NP completeness, and here to establish NP completeness of graph coloring, we can mathematically define a reduction from a known NP complete problem such as a Boolean satisfiability problem that is SAT to the graph coloring problem. This reduction shows that if we have an efficient algorithm for graph coloring, we can solve SAT efficiently as well, which implies that graph coloring is at least difficult SAT problems. Next, we move on to approximation algorithm. I think I can give a small example of why we use approximation algorithm. See, buying a house in a city is very difficult with the amount of money what we have in hand. So instead of buying a house in the city, we'll be searching a house closer to the city, that is outskirts. So the amount of money what we have in hand will definitely fetch you a house nearer to the city, but not inside the city. So inside city, we call this as efficient, and nearer to the city, we call this as approximation. So approximation algorithms aims to find solutions that are close to the optimal within a certain bound. In the case of graph coloring, we can mathematically define an approximation algorithm that guarantees a coloring using at most k times the optimal number of colors. By mathematically formalizing graph coloring problems, decision problems, time complexity analysis, computational complexity classes, and approximation algorithms, complexity theory provides a rigorous framework for studying the inherent computational difficulty of graph coloring and guiding the design and analysis of efficient algorithms. Now we are moving on to session 4, advanced topics in graph coloring. So let's discuss the advanced topics related to graph coloring, which we can include K colorability, chromatic number, and planar graphs. So let's move on to the first one, K colorability. A graph G is said to be K-colored if it can be properly colored using at most K colors, where no two adjacent vertices share the same color. The decision problem associated with K colorability is denoted by K coloring. And given a graph G and a number of K, and a number K is G a K colorable one. The K colorability problem becomes more challenging as K decreases. When K is equal to the minimum number of colors required for proper coloring, the problem is equivalent to finding the chromatic number of the graph. Next is the chromatic number. The chromatic number of a graph G denoted by chi of G is the minimum number of colors required to properly color the vertices of G. Finding the chromatic number of a graph is a fundamental problem in graph theory and has practical applications in various fields. And determining the chromatic number is an NP-complete problem, meaning no efficient algorithm is currently known to solve it in the general case. However, for certain classes of graphs, such as trees, bipartite graphs, and the chromatic number can be computed efficiently. Next, we move on to planar graphs. A planar graph is a graph that can be drawn on a plane such that no edges intersect except at the endpoints. The planar graphs have important properties in terms of graph coloring. The four-color theorem states that every planar graph can be properly colored using at most four colors. And this theorem was proved using extensive computational methods and represents a significant result in graph theory. For planar graph, the chromatic number is at most 4, which makes them particularly interesting from the coloring perspective. These advanced topics in graph coloring helps us to learn the complexity of determining the number of colors required for proper coloring, exploring the chromatic number of graphs, and considering special classes of graphs such as planar graphs. They provide a deeper insights to find and challenges involved in coloring graphs and understanding the properties of different color graph structures. Next, we move on to the next special cases of graph coloring, including bipartite graphs and interval graphs. So let's pick up the first special case of the graph coloring, that is bipartite graph. A bipartite graph is a graph whose vertex set can be partitioned into two disjoint sets such that there are no edges between vertices within the same set. And mathematically, we go for the definition G is equal to V comma E is a bipartite if we can partition the vertex set V into two sets, namely V1 and V2, such that every edge in E has one endpoint in V1 and another endpoint in V2. Bipartite graphs have a chromatic number 2, meaning that they can be colored using only two colors. This property arises from the fact that there are no adjacent vertices within the same set, so no conflicts occur when assigning colors. Bipartite graphs are widely used in various applications such as modeling relationship between two distinct group of entities, representing scheduling problem, or analyzing network flow. Next, we see about the interval graph. An interval graph is a graph that can be represented by a set of intervals on a real line, whereas each interval corresponds to a vertex and two vertices are adjacent if their corresponding intervals intersect. So mathematically, again, we go for the definition. A graph G equals to V comma E is the interval graph if there exists a set of intervals I such that V equals to Vi and Vi comma Vj belongs to E if and only if I and Ij intersect. And interval graphs have a rich structure that allows for efficient graph coloring. The coloring of interval graphs can be done in linear time using the greedy coloring algorithm, where the vertices are ordered based on the endpoints of their corresponding intervals. This property makes interval graphs particularly interesting from a graph coloring perspective, as it provides a computationally efficient way to find optimal coloring. Interval graphs find applications in various domains, including scheduling, resource allocation, and interval-based data representation. Understanding these special cases of graph coloring, such as bipartite graphs and interval graphs, provides insights into specific graph structures that allow for efficient coloring algorithms or to have distinct coloring properties. It allows for the exploration of different graph colors and their applications in solving real-world problems efficiently. Graph coloring has been an active area of research with numerous developments and applications. So here we are going to have some important research, development or applications in graph coloring. So let's start with graph coloring algorithms. So nowadays, researchers continue to explore and develop efficient graph coloring algorithms, including exact algorithms, approximation algorithm, and heuristic algorithms. New algorithm techniques such as meta-heuristic approaches, constraint programming, and local search methods have been applied to improve the quality and the efficiency of graph coloring solutions. Next, we move on to graph coloring and network design. Graph coloring plays a crucial role in network design nowadays and optimization problem. Efficiently assigning frequencies or channels in wireless communication networks requires graph coloring techniques to minimize interference and optimize network performance. Graph coloring is also applied to solve in areas like transportation network, power distribution network, and social network analysis. The next one, we are moving on to graph coloring and scheduling. Graph coloring is closely related to scheduling problems where tasks or events need to be allocated to limited resource or time slots. Researchers have studied graph coloring algorithms to address scheduling problems in various domains such as job scheduling, task allocation, examination time scheduling, and workforce scheduling. Graph coloring and VLSI design. Graph coloring is widely used in VLSI, that is very large scale integration design, to solve register allocation problems. Register allocation aims to minimize the number of registers required to execute a program, and graph coloring techniques are applied to allocate registers efficiently. Next, we move on to applications in social and biological networks. Graph coloring finds applications in analyzing social networks where nodes represent individuals, and coloring can be used to identify cohesive communities or study network dynamics. In biological networks, graph coloring is used to model and analyze gene regulatory networks and protein interaction networks and metabolic networks. And graph coloring and game theory. Graph coloring has connections to game theory too, particularly in the study of competitive graph coloring games. Researchers have investigated graph coloring games where players aim to minimize the number of colors used or to disrupt the colors of opponents, leading to interesting strategies interaction. These developments and applications demonstrate the wide-ranging impact of graph coloring in various fields. Ongoing research efforts continue to advance the theory and applications of graph coloring, leading to improved algorithms, optimization techniques, and insights into complex real-world problems. In conclusion of this session, graph coloring is a fascinating topic in graph theory. With practical applications in various domains, it involves assigning colors to the vertices of graph while satisfying certain constraints such as ensuring adjacent vertices have different colors. A chromatic number of a graph represents the minimum number of colors needed for a proper coloring, and graph coloring problems are also known to be computationally challenging, with the determination of the chromatic number being NP-complete problem. And researchers have developed various graph coloring algorithms, including greedy algorithm, backtracking algorithm, and meta-heuristic algorithms like genetic algorithms. And these algorithms aim to find optimal or near optimal colorings of graphs. The study of graph coloring goes beyond theoretical aspects. It has implications in network design, scheduling, wireless cycle science, social network analysis, biological networks, and ring theory. Researchers have explored applications in wireless communication, transportation network, job scheduling, gene regulatory networks, and many more. Graph coloring has also served as a foundation for understanding and solving complex problems in graph coloring. So now we are moving on to session 5, conclusion and further reading. For those interested in deeper knowledge into the mathematical aspects and applications of graph theory, graph coloring, the following resources provide valuable insights. Graph Theory by Raynaud. This book offers a comprehensive introduction to graph theory, covering fundamental concepts and advanced topics, including graph coloring. And the second one is nothing but the Handbook of Graph Theory, edited by Jonathan and Ross. This handbook provides an extensive collection of articles covering various aspects of graph theory, including graph coloring and applications. An introduction to graph theory, Douglas West. This book provides an accessible introduction to graph theory, including a section on graph coloring and related algorithms. Graph coloring problems, edited by Tommy Jensen. And this focuses especially onto the graph coloring problems and their applications in different fields. It covers both theoretical aspects as well as practical algorithm. And algorithmic graph theory and perfect graph by Martin Charles and Golubic. This book explores the graph coloring and its relation to perfect graphs, representing algorithmic approach and highlighting application. These resources provide a solid foundation for understanding the mathematical knowledge of graph coloring, its computational challenges, and its practical application in diverse fields. So basically, we were learning graph coloring using algorithmic way. Nowadays, the most of the technology improvement, we can jump into the concept of programming languages also in graph coloring. Maybe we can have the time complexity and the space complexity comparison in our research paper so that we can also grow along with the society, along with the mathematical world and computer science world with the most popular programming languages, namely C++, we can have, or we can have Python programming. Along with algorithmic approach, if we apply the programming languages also into the graph coloring, I think the future graph coloring world will be flourishing more. Thank you so much for the opportunity. Thank you.
Thank you, ma'am. Thank you for delivering such an insightful and engaging lecture on graph coloring and complexity. Your your expertise and passion for the subject truly through, and we are grateful for valuable knowledge you have shared with us today. Your comprehensive explanation have provided us with a deeper understanding of the topic. Your research accomplishment and achievement in this field of graph theory are truly commendable, and we feel privileged to have had the opportunity to learn from you. We would also like to thank and express our gratitude to our esteemed HOD and our workshop coordinator, Atul Ray, sir. Their presence has been invaluable in guiding us towards academic excellence. Lastly, we would like to thank all the workshop coordinator, faculty members, and participants for active involvement in and enthusiastic participation. Your presence and contribution have made this workshop a resounding success. As we conclude the first day of the workshop, we look forward to another insightful session tomorrow. Let us carry forward the knowledge and inspiration gained today to the further explore the realms of applied mathematics and computing. And yeah, participants, I have shared the quiz and feedback form in the chat. You have to fill it for further for your certificates and accurate details and participate curiously. Thank you once again, and we eagerly anticipate the continuation of this enriching workshop. Thank you.
Thank you.
You all may leave.